Thank you. Thank you to Mel for the opportunity to speak. It's one of my has always been perhaps my favorite number theory seminar, combinatorial number theory, additive number theory. This is what I like. And as much as I can, I always try to present some work that touches on these subjects. And today I will talk about some results that are really on the interface between combinatorial geometry and combinatorial number theory. Like always, I try to keep talks relatively light in content, so only at the very end will I have some vague description of some arguments that are maybe difficult to follow. In the beginning, I will have a relatively short argument that I hope people will appreciate. But yeah, that's the plan for today. And if I finish early, I finish early. I actually have another meeting at 4, so I need to attend that one. So everything I will say that is new, because some of the things are actually pretty old, but everything that I will say that is new is joint work with Oli Roche-Newton, Misha Rudniev, and Odi Warren. I will make sure to repeat those names when I state a theorem. But in fact, there is, our work builds on very well-known and sometimes relatively old work of many people, Beck, Elekes, Helfgott, Land, Schaeffer, and Dezev, Zhao, Murphy, Skredov. So a lot of people actually have, or maybe I should say that our work really builds on interpreting the work of these previous researchers and probably even more people. So the seminar will come in 2 parts. The first will be actually kind of self-contained, and I think hopefully the one that more or less everyone will be able to follow, and it will be a way to answer in the affirmative question of Yufei Zhao. That's what I referred to in the title. The second one will get just a tiny bit more technical. We'll talk about the energy, whatever that is. I'll define it in the affine group. There's some things you just have to take it on trust. It's very simple things that I have not done derivations. You can take it on trust. And maybe at the end, when I give the argument, maybe just follow the gist, that will be enough for me. Yeah, so that's the basic idea. It comes in 2 parts. So I'll just go ahead and start with the first one that is motivated by one of the central questions in combinatorial number theory, the sum product conjecture of Erdos and Semeredi. And I never tired to remind everyone that for a period, Mel was the record holder in this conjecture. So to make the connection apparent, I'll just take it easy on this first slide. So we start with a finite set of reals, and from this set, we construct the finite points on the parabola y equals x squared. So for little a in big A, we'd consider the point a comma a squared. Okay, so we have a finite point set, and then we look at the collection LP of lines that are determined by this point set. Of course, to determine a line, you mean that there are at least 2 distinct points from the point set that are incident to the line. I mean, there's no point to say only 1 point, because then you can have infinitely many lines. But once you have 2 points that determine a unique line. So this is what we mean by this set LP. And then if you just consider this set for these finite point sets that is on the parabola, you see that the lines, so the line that goes through the point a comma a squared and b comma b squared has a very nice looking expression. It's y equals a plus b times x minus ab. So what you see is that the collection of lines in LP have a slope that have slopes that come from the sum set of A, and they have y coordinates that is minus the product. So the very famous conjecture of Erdos and Semeredi is that either the number of sums or the number of products is considerably larger than the number of elements in the set. So this tells us that for this particular point set, if you look at the y-intercepts or the slopes, at least one of those 2 sets is considerably larger than the point set. And an informal, no, sorry, not informal, another way to interpret this, the y-intercepts and the slopes, is to think of the intersection of these sets of lines with two lines. One is the y-axis, these are the y-intercepts, and for the slopes, you can think that it's the intersection with some line at infinity. So basically, this was probably an observation that many people have made, and sorry. So I will state it carefully in a second, but Yufei Zhao asked whether this always happens. So if you have a point sin that is not on a line, so something like the parabola, is it always the case that it's the intersection of lines in LP with two other lines, at least one of the two is much larger than the number of points? So this is here a very badly drawn slide, but basically tells you, you have the points in the parabola on the left side of the slide, then you determine a line when you have two of them on them, and then on the right-hand side is what cannot happen somehow, so that you simultaneously have very few slopes and very few y-intercepts. So that's basically Zhao's question. So specifically, this is the question that he asked. So he says, given a constant that is absolute, let's say initially little c, it can be very small. Does there exist another constant, capital C, with the property that whenever you have a finite point set P in R squared, and you have two distinct lines, L1 and L2, and the property of the point set is that it has few collinear points. So at most C, a proportion of C points lies on any given line. So under this hypothesis, is it true that LP, the set of lines determined by P, must intersect either L1 or L2 in at least capital C times P points? So if you take C to be 1/1000, the question is, can you find the capital C that is like relatively large, that has this property? And again, let me say the obvious thing, that the non-linearity condition is important, because if the points are on a line, then they determine one line and you're done basically. So you need some kind of collinearity condition, non-collinearity condition, I'm sorry. And I guess, yeah, so in a joint paper with Roche Newton, Rudniev, and Warren, we answered this in the affirmative. We said the answer is yes. In fact, we could do much better than having absolute constants. You can take C to be the number of points raised to some power minus delta, and then the value of capital C is basically the number of points raised to the delta over 14. So you see a very explicit connection between capital C and little c. One is a power of the other, not some kind of like crazy exponential of tower of twos or something like that. So there's a very nice polynomial dependence. And also, you don't need them to be absolute, like they can tend, like little c can tend to 0 as the size of the set tends to infinity. So this is what I would like to actually prove completely, because that was a question that, now 5, 6, 7 years ago was relatively well known. So I'm just going to actually give you a full proof. And it's actually, I don't think it's that bad. And I'm going to use two theorems from geometry, both due to very accomplished Hungarian mathematicians. The first one is one of my favorites, is Beck's theorem. It's called like the two extremes. So what Beck's theorem says is that there is some parameter eta. You can think it of being like, you can, if you don't try very hard, you take it to be very small. If you try hard enough, then you can take it to be a bit larger. But anyway, there is some parameter eta with a property that if you have any finite point set that has, again, few collinear points, so the number of collinear points is at most a proportion of eta of the number of points, then basically you get a proportion eta p points that are incident to at least eta p lines from LP. So this is this Beck's theorem. So again, it's called the two extremes, because either the point set has many points on a line, or you have many points that are incident to many lines. So that's why it's the two extremes. Somehow, if the point set is random, then you can take eta to be more or less 1. But I guess Beck's theorem says that not only random sets have this property, but any set that does not have many collinear points. So that's the first theorem of Beck. Then there's another theorem of Elekes. It's geometric, but it has a very heavy sum product flavor. And this one concerns a Cartesian product. So not general point sets. You need to have a Cartesian product structure. So again, you
Excuse
take.
me, I'm still puzzled by this theorem of Beck's.
Yes, yes.
There are at least, I mean, let's say this parameter is a half, just for the purpose of, then there no more than half the points are in any line. Then there are at least half the points of the set are incident to at least I mean, each point. I'm not clear on the quantifiers. What's the picture here?
So the picture is, first of all, we don't get to choose eta. Eta is, so the proofs I know given.
Some eta, yeah.
Yes, so they give something much smaller than 1/2, but yes. So the idea is basically just to start thinking about it, take the points all on a circle. Of course, that's a very specific configuration.
Yes.
But then what's going on is that then if you have n points on a circle, they basically determine, well, I can't think now, but probably n lines, right? Yeah, and any 1 point, sorry, so just take them on the circle, then basically every point passes through n-1 lines determined by the point set.
Right.
So that would give you eta to be close to 1, I guess. But so I guess, so that's how you should think of Beck's theorem, that there is a proportion of points that then if you look at the lines that pass through that point and some other points in the point set, well, there can be at most n of them. And what Beck's theorem guarantees is that there are at least eta n of them. So you can draw many lines that contain, let's say, this point and at most 100 more. Maybe that's another way to think of it. Does that help a little bit? No. So again, I think maybe the circle or a regular n-gon is the easiest one. But so you can not you can say, like, but there exist many points that if you draw all the lines that pass through this point and at least one more point from the point set, then a very large proportion of these lines will contain at most 100 other points. I mean, that's what's going on somehow. It's not. It's far from trivial theorem. I mean, nowadays that we know the Semeredi-Trotter theorem, one can prove it easily. But anyway, I think that's the statement. So, or I said before, like a random point. If you throw a random point, random point set, if you throw points on our square on the plane, then there with probability 1, no line will contain 2 of them. So then again, this statement is true for eta equals 1. Okay, so that's Beck's famous theorem. It's one of my favorite, really is. I guess one of the reasons if somebody asks you without thinking, you might say, no, there's no way this thing is true, but it is. But anyway, so Elekes' theorem is another theorem in geometry that has applications to number theory. And that concerns, though, now Cartesian products. I'm not saying 1 all the way up to n cross 1 all the way up to n, but you have a set, finite set A, and you consider A cross A. Okay, and then the point is, again, there is some constant K, like relatively, it's not that large actually, this one, what we can prove. But anyway, there is a K with a property that for all parameters alpha, okay, so if you know that there are at least alpha, sorry, the size of the set, of the finite set is n, so the size of the Cartesian product is n squared. So if you have alpha n lines that are neither horizontal nor vertical, because these can, like you can easily find such heavy lines. So if you have alpha n lines that contain, let's say, at least alpha n points of the set, then basically some proportion of them that depends on alpha, so alpha to the k divided by k of them must be either parallel or concurrent. So if you think now A to be the first n integers, then the parallel lines that are very heavy, you can take they are parallels to y equals x. So many of these guys are they contain many points of the point set, but they are all parallel. And then you can also kind of do the other thing where instead of having 1 all the way up to n, you take powers of 2, 2, 4, 8, 2 to the n, and then these then there are many lines that pass through the origin and they support many points. So it's this sum product feeling again in these geometric theorems. But again, the idea is that in a Cartesian product, if you have many heavy lines, then many of them are either concurrent or parallel. Okay, so now I have these two theorems, and I'm going to use them to prove just give an affirmative answer to the question of Zhao. Okay, so what's going on is we have a point set that has capital N points, and at most little c times n of them are on a line. So little c is given to us, and what I would like to show is that there is a line that intersects LP in at least capital C times n points, where capital C will depend on little c. So again, I do some transformation just to make things easy, and I take L1 to be the line at infinity and L2 to be the y-axis. Then basically the intersection of LP with the first line is the set of slopes. I call this capital S. The intersection of LP with the second one is capital T, the set of y-intercepts.
Just do that.
So this means that the lines in LP have the form y equals sx plus t, where s is little s is in big S, little t is in big T. Okay, so I have somehow like these lines. Okay, so now for contradiction, just to make the argument easier, I suppose that both S and T have size at most capital Cn, and I'm going to get a contradiction if C is small enough. So somehow this means that there will be some relatively large constant capital C that depends on little c, such that either S or T have at least Cn elements, and that's basically an affirmative answer to Zhao's question. Okay, so I have done all this just to set it up. And now I'm going to start, I will first apply Beck's theorem and then Elekes's theorem. So the first thing is, again, I have this point set P, and I just pass to a subset of density eta that has the property that every point is incident to at least eta times capital N lines. So this comes from Beck's theorem. Okay, so now I have to do this confusing thing because my point set is not a Cartesian product. And I want to apply Elekes's theorem, and Elekes's theorem is for Cartesian products. So I'm going to use the duality. So if I have a point P1, P2 on the point set, and a line y equals sx plus t, well, I can reverse the role of points and lines and think of the point s, t that is in a Cartesian product, and this is incident to the line P1x plus y equals P2. So this can confuse us a bit, but I have to do it. So then also I want a symmetric Cartesian product. S does not equal T, so therefore I take their union. So I take the capital A in Elekes's theorem to be the union of S and T. And because I have assumed that both S and T are small, somehow compared to capital N, I can also assume that the size of A that I denote by little n is somehow bounded above by 2 times C times the size of the original point set. So now by Beck's theorem, it's a point in P prime which gives us lines. So we get lines that are incident to at least eta times capital N points in A cross A. And now capital N is, anyway, we take it at least to be N over 2C. So anyway, we get a proportion of eta over 2C. We get a line that is incident to many points. So now I just take the alpha in the Elekes's theorem to be eta over 2C, and I can apply Elekes's theorem because I have a Cartesian product. So okay, I do this, and then Elekes's theorem, remember, has this alpha to the k divided by k times the number of points. So if you do all the calculation, I have written them in the slide, you get on the right-hand side something that depends on capital N, but all the other stuff is basically of two kinds. You have eta and capital K that are just absolute constants. They are given to us from the theorems. And then you have this expression capital C that you have control on. So when you take capital C to be, sorry, what am I doing? Yeah, so when you take capital C to be large, you can make this expression being bigger than little c. So what does this mean? This means that you have this at least C capital N lines that are either concurrent or they're parallel. And the whole point is concurrent lines, because of the R of the form, if you go back to the previous slide, P1x plus Y equals P2. So, so that means, sorry, parallel lines, I'm not very sorry, parallel lines means P1 is the same, is constant. So that means that your original point set has many points where P1 equals constant. So this means that the original point set has many points on a line X equals P1. And that's not allowed. Remember, the original point set has at most C capital N points. So that happens with parallel. With concurrent, then if you have many lines that pass through the line S comma T, then that means the original point set had too many points on the line Y equals SX plus T. And that's again a contradiction. So basically, yeah, that's basically the end of the proof. And everything I have done here has powers, right? So Beck's theorem just has constants. Elekes's theorem has this capital K that can be explicitly computed. I guess that's something we did, and it's not that big. So this is why you get this power dependence between little c and capital C. So anyway, it's just this. So to answer, maybe the takeaway is to answer Zhao's question, you need to use Beck's theorem and Elekes's theorem, and then the argument works. So now I'm going to move on to the second part of the talk, that is going to be discuss actions of the affine group on R squared. So here, I think, things are somehow like, if one doesn't have a lot of exposure before, then it might be a little bit hard to confirm everything in real time. You can just accept that I have done all the calculations at the back of an envelope. So the connection with the previous theorem is that we proved this theorem basically initially at least using these properties of the affine group. Then we found this shorter proof that I presented. And so in my mind, the two topics are related. So, okay, what is the affine group of transformations? You take a point X and you map it to Sx plus T. So that's like an affine transformation. You can also think of it as lines. So you think of the image as Y, then the line is Y equals Sx plus T. You can also think of it as matrices. So you have the column vector X comma 1, and you multiply it with the matrix ST on the first row, 0, 1 on the second row. And this gives you Sx plus T on the top component and 1 again in the bottom component. So you can also think of it as somehow like a matrix group. And basically, as you probably imagine, because we have matrices, the composition of these two affine transformations corresponds to matrix multiplication. But now, I guess to visualize what's going on, it's definitely not only us, a lot of people have been doing this decades before us. You can visualize the affine group as points on the plane. So S comma T, which is an affine transformation, X goes to Sx plus T. You can also think of it as a point on the plane, as the point S comma T, I guess. So then there is this somehow duality. So a finite set or just a set of affine transformations corresponds to a set of points in R squared. So now I would like to discuss a little bit subgroups here because they play an important role. So let me just say here, the catch is that subgroups of the affine group correspond to lines on R squared. So remember, when you map an affine transformation to a point, then you map basically a subgroup to a line. So what's going on is, first of all, the first very easy subgroup is translations. So you send X to X plus T, or if you like, Y equals X plus T, this transformation. And this corresponds to the line. So what's going on here? So your S is always 1 and your T varies. So if you try to draw it on the plane, then the group of transformations corresponds to the line X equals 1. And now the one thing that I want you to just take it on trust, if you look at the stabilizer of U, it's just a very quick calculation, but this corresponds basically to the line Ux plus Y equals U. So it corresponds on R2 when you draw transformations as points to a line that has slope minus U and Y-intercept U. And these lines for all U pass through the, this is called the identity transformation, 1, 0. It's the identity transformation because then X is sent to 1 times X plus 0. So then the other thing that's going on is that cosets of subgroups also correspond to lines. So with this in mind, I define this important property for us, because in the affine group, we have subgroups, and we need to be able somehow to tell in a quantitative way how close is a general set of transformation to a subgroup. So what interests us is how many of the points of the set of transformations, or when you map 2R2, how many points of the point set are on a line. Sorry, when you talk about transformations, you want to know how many of them lie on a subgroup. When you draw the picture, you want to know how many points are on a line. And we're going to call this parameter capital M. And this is going to be quite important in what follows. So here's a picture, a very bad picture again of the subgroups. So the one that is parallel to the y-axis is the translations. So the line x equals 1 corresponds to translations. And then the other line is the stabilizer of a point u. So it always passes through the identity transformation, 1, 0. Again, this is x goes to 1 times x plus 0. And also, it passes through the other boring transformation where x is sent to 0 times x plus u. So all x are sent to u. So basically, the stabilizer contains these 2 points, and it actually corresponds visually to a line. So these are 2 types of subgroups somehow. So there is this back and forth between somehow like when you draw things on the plane with geometry and with the algebra, with when do you have a subgroup? So yeah, the object that we studied, and we were definitely not the first, is the so-called energy in the affine group. So for those with a background in additive combinatorics, you can think of this as a generalization of additive energy or multiplicative energy or something like this.
Why the word energy?
That's a very good question. So I can't really say myself, but what happens here is so there is the definition that is on the next line of the slide, and you see this is symmetric. So you have G1 inverse composed with G2. So you can think that this guy, you're interested in how many ways does a general transformation. So if you have G1 inverse composed with G2 equals some other transformation G. So the additive energy counts the sum of the squares of this representation. So you have a function and you compute its square. And I guess from physics, if you think like kinetic energy, this kind of stuff, these things usually correspond to energy. I don't know how this was coined. I personally find it kind of like a confusing terminology, but it is really widespread.
It starts with tau and vu. I mean, where does it start? The terminology, do you know?
I would think along, yeah. I'm not saying anything because I haven't looked into it, but yeah, definitely, yes,
Okay.
yes.
So you think it really has some origin in physics, in some interpretation or another, it really represents energy. Or yeah.
No, because these are like number theory. No, just because it's a sum of squares, I think. And then in physics, very often we have integrals of squares and its energy.
Yeah. I mean, the concept's been around for a long time. You're just looking at elements that have multiple representations. And I think it was Tao and Vu who might have introduced the term energy, only because you see something quadratic, you see a square, but I don't know of any connection to anything physical.
Yeah, so I definitely agree with Mel on that. I mean, like I said, I personally find it a bit of a confusing terminology, but it's really widespread. It's impossible to change it now, I think. So anyway, so what we're counting is again the number of quadruples, G1, G2, G3, G4, whether all elements of this set of transformations, such that G1 inverse composed with G2 equals G3 inverse composed with G4. So again, what is the trivial upper bound of this quantity? Well, if you are given G1, G2, and G3, there is actually a unique G4 in the affine group that satisfies this property. So somehow, like the worst thing that can happen is that this G4 is in the set of transformations. So the absolute maximum that this energy can be is the cube of the number of transformations. And in fact, now you see very quickly you get equality when lambda is a subgroup. So if it's a subgroup, it's closed under all these operations. So whenever you're given G1, G2, and G3, there is a G4 in lambda that satisfies this. So this means we have an upper bound that is attained in some examples. So maybe, okay, in some way, the question is completely solved. We have like a trivial upper bound in this attained. But what's interesting is to introduce some more quantitative information on how close you take lambda to be to a subgroup. So this is why I introduced earlier this quantity capital N that is basically the number of transformations in lambda that belong to a subgroup. So it's the maximum number of maximum intersection of lambda with a subgroup, if you like. So then what I am about to show you, that was our aim, was to find a an upper bound for this quantity that involves capital M. Okay, when capital M equals the size of lambda, when this is the case, then our bound should really be the cube of the size of lambda, because that's what happens. So we cannot get rid of this dependence, but we want to have some upper bound that when lambda is small is a lot better than lambda cubed. And something that is worth saying, oh yeah, Kevin has actually put something in the chat. I'll check it after I'm done. So something else that's interesting for those that have thought a little about combinatorial geometry is that there is some connection with what I'm about to do with this concept of bisector energy, another energy term here that is coming, and that was introduced by Lanz, Scheffer, and Desev. And basically, this is the number of isosceles trapezoids that have vertices on the points that you get from the transformations. Okay, so there is some connection. I'm not going to go into great detail with this. So let me just say, though, again, take it on trust that this is how it works, that there is a way to visualize this affine energy. It's not exactly isosceles trapezoids, though. But if you have basically these four transformations, such that G1, G2 inverse equals G3, G1 inverse G2 equals G3 inverse G4, then what happens is that you get lines, the lines that pass through G1 and G3, and the line that passes through G2 and G4 have the same y-intercept. So you just do some algebra and this comes out. And the other thing is that the line that passes through G1 and G2 and the line that passes through G3 and G4 is parallel. So you do have like some geometric thing which we actually use in our arguments. So I have introduced this concept. I have given you a geometric way to visualize it. So obviously here what's going on is you have so lambda gives points on the plane, and then you try to find how many configurations are there like this that I described, so that you have lines that, two of the sets of the lines pass through the same y-intercept, and then the other two are parallel. That's the question. So why are we interested in this? Well, starting with Helfgott, although that was a baby thing in his paper, people are interested in growth in the affine group by applying the Cauchy-Schwarz inequality. So what does growth mean? You start with a set of transformations. If it's not more or less, if it doesn't have huge intersection with a subgroup, you expect that when you take lambda inverse composed with lambda, you get a much bigger set. And in order to prove this, you can apply the Cauchy-Schwarz inequality, and you see that if you have small additive energy, which is where I'm going to, then you have growth in the affine group. Another one is the sum product question. So this is like the L2 version, if you like. So L2 now mean like physics or an energy version. So you have a finite point set and you want to count the number of solutions to the equation A1 plus A2 times A3 equals A4 plus A5 times A6. So again, the trivial upper bound here is size of the set raised to the 5th power. But you expect that this will never happen. I mean, of course, if we had subfields in the integers, then a subfield would have A to the 5th solutions. But there are no subfields in the integers, so we really expect that we can do much better than the trivial upper bound of A to the 5th. And then what is going on here is that, for example, using the Semeredi-Trotter theorem, or just some point plane incidence theorem, it was possible to prove an upper bound of size of A times the exponent, raised to the 4.5. So 5 is trivial, 4.5 comes from incident geometry. And it was a long-standing question to be able to improve the exponent by an explicit constant. And this was achieved by Skredov and Rudnev, who showed that the number of solutions is at most some constant C times the size of the set raised to the power 4.5 minus this C. And that was like, I think was a, I mean, not some major breakthrough, but it was a definite step, something that, I myself had tried and I didn't manage. And it's worth saying that this is somehow, again, some energy or L2 version of another, this was truly, I think, a breakthrough, earlier result of Roche Newton, Ruza, Shen, and Skredov, who showed that if you take any set and you consider all elements of the form little a plus little b times little c, then you get considerably more than the size of the set raised to the 3/2. In fact, the improvement is by something in the exponent. So Roche Newton, Ruza, Shen, and Skredov were able to prove this. That was, I think, a great paper. And this actually then follows via the Cauchy-Schwarz inequality, follows from the later result of Rudnev and Skredov. So Rudnev and Skredov used affine energy. So therefore, I mean, I'm just trying to explain that this kind of concept has applications in some product theory. And it also has, as I have already hinted, applications to combinatorial geometry. So for example, using it, we were able to prove some pretty decent bounds, quantitative bounds for Helmholtz's theorem. So again, polynomial. If you remember in the earlier slide, I had said that you can take little c to be like a polynomial, like a power of little c, of the reciprocal of little c. And we also used it initially to prove the, to answer the question of Yufei Zhao, although later on we found this simpler argument. So yeah, let me now, let me start giving you some history. So the result of, I have already said that Skredov and Rudnev used this energy in the affine group to prove some interesting stuff. But there was one peculiarity in their argument, that the point set that they took, or the set of transformations, came from a Cartesian product. So you really needed this Cartesian product structure. And then they proved an upper bound that is of the form, the energy is, again, lambda cubed is trivial. But when you have a Cartesian product, they were able to reduce the 3 to 11/4 minus a constant c. And then c is some kind of like very small number, but it's absolute. And let's just say that 11/4 was known and easy to obtain nowadays. And they were able to improve this exponent by this little c. By the way, I'll just go back to the previous slide. This little c is also then what gives them the improvement over what you get from Samaretti-Trotter in the result about sums and products. So anyway, that's what they did. But it was for Cartesian products. In a Cartesian product, also the number of points on any line is at most the square root of the size of the set, because I mean that's just some obvious fact. So you can think that maybe for their result you don't really need this quantity capital M, because this is, I mean, you will never have, in a Cartesian product that is symmetric especially, you will never have many points on a line, too many points on a line. So this is historically what Skredov and Rudnev have done. And I guess what we did is we generalized the result. We didn't get as strong a result as theirs. I will say this more on a moment, but we were able to obtain some kind of like non-trivial result for general point sets. So we no longer assume this Cartesian product structure. And for those of you that work in this geometric stuff, I mean, you know that there is a distinction between the two. So somehow things are a little easier when you have Cartesian products. Sometimes people ask me, what do I think is the truth? Well, if you look a little bit the connection with this work of Lan, Scheffer, and Dezev and examples that we have thought of, it seems possible, maybe up to some logarithms or powers of lambda to some epsilon or something, that the correct answer is that the energy is bound above by the product of this quantity m and then the square of the size of the set. So when m equals the size of the set, you get m cubed when you have a subgroup. And when m is very, very small, you get an almost minimum energy, right? So the energy is always at least size of L squared. So anyway, this is, I don't know, I won't call it a conjecture, but I have thought a little bit and I can't think of examples that contradict this claim at the end of the slide. So let me now state the theorem. Again, remember, I'm trying to prove something for all point sets, and there needs to be this parameter capital M that measures how close we are to a subgroup. So the upper bound we have obtained is the explicit one of the form, this parameter m raised to the 1/2, then the number of transformations raised to the 5/2, and then you have the other term that I kind of think is perhaps the truth. You have the parameter m multiplying the square of the number of transformations. So again, you see here when when this parameter m equals the number of transformations, this is trivial. You just get lambda to the cube. But once it's considerably smaller, well, I have hidden there is an absolute constant in front too. You don't get just a strict inequality. There's like some explicit constant, but I haven't written it down. So that means that when the number of points on a line or the number of transformations on a subgroup is much smaller than the number of points, but much smaller by a constant, then our result becomes non-trivial somehow. And yeah, we prove this over R, but the same argument actually is true for any field, the complex numbers, for example, but also for finite fields or infinite fields of positive characteristic. But once you start entering positive characteristics, you have to be careful because somehow these, anyway, there are subfields, and this creates problems. So you need to make some assumptions that rule out subfields, and the one we need in our proof is that this product of this parameter m with a number of transformations has to be smaller than the square of the characteristic. Just think of this as some technical term that does not allow bad things to happen. But something worth saying here, just to go back to Skredov and Rudnev, so let me just show you, is that they had proved exponent 11/4 minus some constant. Now, if you go to our theorem, remember m in their case is the square root of lambda. So we get 11/4. So actually for Cartesian products, we did not improve the state of the art. That is due to Rudnev and Skredov, but we proved a result that is true for all point sets somehow. So now we'll just say some things about the sketch. It's 11:43 already. I'll just sketch the proof. It's just like, you just need to follow your nose a little bit. So again, I'm going to write these transformations gi as si comma ti. So if you have g1 inverse composed with g2 equals g3 inverse composed with g4, I mean, you just need to use the matrices, let's say, and do calculations. And what you get is that the reciprocal of S1 multiplying S2 equals the reciprocal of S3 multiplying S4. And I can also write things as products. So S1 times S4 equals S2 times S3. So, so that means that if you have like this sort of energy quadruple, then you get like a multiplicative quadruple in the first component. So then what we do is we basically break up the energy according to which value these products S1 and S4 comes. So for every quadruple G1, G2, G3, G4, S1 times S4 and S2 times S3 equal some number. So we break it up according to this number. We call this number G. So this means that the energy is the sum of overall Z of the number of quadruples that satisfy G1 inverse composed G2 equals G3 inverse composed G4, and also S1 times S4 equals S2 times S3 equals Z. So we have that the energy is the sum of some other quantities QZ. So now I just have to calculate QZ, and this is again where you have to trust me, but again, you go into the matrices, you do calculations and all that, and somehow what pops out after some steps is incidence geometry, a lot like the Elekes style. So what's going on in this situation is that you end up counting the number of incidences between a set of points and a set of planes. And the set of points and planes, they're not the same, of course, in any way, but their size is the same. And the size is this, the number of these pairs that I call curly CZ, that is, let's say, the number of pairs G1, G4, that both are elements of lambda, such that S1 times S4, so the slope, if you like, of the first times the slope of the other equals Z. So again, by doing some algebra, you reduce to counting the number of incidents between CZ points and CZ planes. And now you can use incidence geometry. If you work over R, then you use a result of Elekes and Toth. maybe some earlier ones too. I mean, this is the one that I consider to be the most general. If you work over general fields, then you have to use a result of Rudnev and then worry about what the characteristic does if you are in positive characteristic. But anyway, you apply, let's say, the theorem of Elekes and Toth, and you get that QZ is at most the number of these pairs CZ raised to the 3/2 plus M, this M that comes from the big set times the size of CZ. And now, because later you will see we have control over the sum of the CZs, I need to put an upper bound. So I break CZ to the 3/2 as the maximum of CZ raised to the 1/2, and this is lambda. And then so lambda, sorry, M times lambda, and then I'm left with one more CZ. So again, what I have done from the first line to the second is I have said that CZ is at most M times the number of transformations. So now I have this, remember, to get the energy, I just sum over all Z. So I sum this inequality. When you sum over all Z, the CZs, then just by looking at here, you're summing over all Z to the number of these things. So anyway, you get the size of the set squared. So that's the last thing. The sum of the CZs is lambda squared. And that basically gives you the proof. Okay, it got a bit messy and a bit technical. I have skipped some steps. But again, maybe the takeaway is that in order to bound the affine energy in the the energy in the affine group, you do some calculations, you use matrices, and somehow this, which happens a lot, like this, you can reduce this to a point plane incidence question, and then you use some known results of Elekes and Toth or of Rudnev, and you get our result. So I think, technical slide as it may be, this is a good moment for me to stop and to thank you for your attention.
Thank you, Giorgis. Any questions for our speaker? Such a quiet group. Questions? Yes, no. Let's see. Oh, there he is. Well, I don't know what it's like where you are, but in New Jersey, it's a beautiful day. So I hope everyone is enjoying the day. It's lovely. Next week, we are on spring break, so there's no seminar. So our next seminar will be 2 weeks from today. And I know there's always a great competition to speak, but if someone wants to put in a special request, let me know. Yes.
Yeah, so I have this faculty meeting in 10 minutes, so I will leave. But again, thank you to everyone for attending and to Mel for the opportunity to speak.
Thank you
Many
very much,
thanks.
Giorgis. It's great to see you.
Thank you.
Bye. Okay. That seems to be it, everyone.
Have a relaxing spring break.
Yes. So for us who teach on Zoom, it's hard to distinguish spring break from the semester, but but it's a chance to catch up on some work and write up a paper or two, whatever, just get the things going. I hope this weekend my son will be home and he will reconfigure my Kant website so I can, it will start saying Kant 2022 instead of Kant 2021. I mean, it takes him about 10 seconds to do this, but you have to know 10 seconds of computer stuff more than I do in order to do it. So, because several people have asked me about this, and we have the dates and it's all very simple, but hopefully by Sunday I will have the website for Kant 2022 online. Okay, everyone.
See you
Yes.
guys. Bye.
Thank you, Mel. Be well.
Thank you, David.
everybody. Thank you.
Hag Sameach.
Hag Sameach.
Everyone be well. Bye.
Bye.